Hi, everyone. I want to take a minute to talk about specifically a visualization for machine learning and for statistical modeling. So there's a lot of ground to cover here, a lot of different ways that visualization interacts with machine learning and modeling in general. And I want to start with some of the kind of the standard plots that are used for modeling. So one of these, if you've ever taken like maybe a first, second semester statistics course in undergrad, and you also will see these show up. These are maybe more old school, but these are still super useful if you're building linear models, and will show up in kind of that first statistics use of linear models. This is called a QQ plot, and the idea here is a very specialized plot to look at whether a distribution follows how closely it follows a normal distribution. Not to dive too deeply into how the specific plot works, but here's an example. You have some theoretical quantiles of data, and then you plot your data against that. So this is a diagnostic graphic that would be used when you're fitting specific classes of statistical models. So this is just one of a handful of these type of diagnostic plots that you could use for linear models. So you'll see these type of visualizations show up a lot in that introductory statistics space and in the linear modeling space, and these are often built in R, the language that is commonly used for doing some of the statistical modeling. But of course, you can build these in any of the tools that we've seen. These are just one of the first plots. Another pretty common use case that I saw in the marketing space in particular is, that is also in the this one's in the model assessment space, is a AUC ROC curve, right? Some people call it AUROC, some people just call it an ROC curve. But what they mean is this plot on the top here, right? And the metric which is associated with it is the area under the curve, something between 0 and 1, the percentage of that actual unit square that is covered. And the idea behind this plot, right, is if you have some model, this would work for logistic regression or any type of classifier that's outputting a continuous score. If you vary your decision threshold from 0 to 1, so a model score of 0.4, is that positive or negative, right? You have to set some threshold. So whether it's above or below that threshold determines whether it's predicted true or predicted false. And so you vary that threshold from 0 to 1. At 0, your model is going to predict all trues, right? And then at 1, your model is going to predict all falses. So between there is going to be some threshold where your model balances between false positives and false negatives. So as you vary this threshold, the false positive rate and the true positive rate are going to change together. So the green line here is starting at the bottom. Actually, you'd start at the top if you set your threshold at 0, and as you move your threshold for your model down, you're going to trace out this ROC curve, which is going to be each point on the ROC curve is a specific threshold on your model, and the true positive and the true positive rate and false positive rate at that threshold. So this is a pretty common diagnostic plot as well for not any specific model type, but models that are outputting things on a 0, 1. And it gives you an idea of just the overall performance of the model. The AUROC score, right, also gives you a sense for the overall performance of the model. Just one metric and another kind of common plot. There's, as you dive into doing more modeling, or if this is something you've done more in the past, the types of plots for diagnostics in these, there's a lot of options, and you can really go in different directions. This is one that I was going to talk about. I see in the marketing spaces, these ideas of lift and gain charts are. When I was working doing data science for marketing, this is the kind of plot that our stakeholders were used to, and that we actually ended up producing a lot of are these lift charts. So maybe bin your model by the decile, so the top 10%, 10 to 20%, and then plot the ratio of positive hits in that decile over the total number. You can also compare it to random. That's the lift chart on the bottom. And the gain chart, right, is actually just the cumulative version of the lift chart. So these are both kind of common, and the idea here, it makes sense in that space, is that, like, well, if I'm going to send an email or email everybody maybe, but you want to send a mailer in the mail to 10% of your customers. What's going to be the hit rate versus just sending it randomly if you use the model? So here on the bottom lift chart showing if you use your model, 4.5 times as many hits are going to happen in that top 10% versus distributing it randomly. So pretty common chart there, and these are, you can do deciles, you can do bins of 5%, and another kind of common chart to do there. Another one, if we want to dig into understanding the models themselves, are feature importance. And so this is actually looking at, I think this is going to be a matplotlib plot built on top of a scikit-learn for doing feature importance for a random forest. So feature importance for a random forest is, there's a few different ways to go and actually generate the values here. But in the end, it's actually a pretty simple plot. It's just a bar chart by feature. So features on X, and the importance on Y. Here also, it's a random forest, so you have 300 individual tree classifiers with different features, and so there's some standard error on how much those on how important those features are. And a pretty common one for looking at for, again, doing model diagnostics and understanding which understanding the internals of models and how it's performing. This one's specific to a random forest. You can think of the feature importance for a linear model as just being the coefficients. And there's ways to get at feature importance for any type of model. One of those, the next one I'm looking at, is doing that for a neural network. This is a visualization of a neural network's classification performance, right? And here you can go and you can look at how each node in that neural network, each neuron, is the activation function at that neuron contributes to the final score for the model. So this is taking beyond just feature importance, taking a deeper dive into the individual components of the model to see how they perform. This allows you to explore and dive in a little bit, and this is from TensorFlow by Google. They've also taken neural networks and done really deep exploration. So answering the question, why is my model giving a particular score, right? You can really dive in and for these vision neural models, right? They've actually done some really cool work, and you'll have the links to these to look in more depth. I'll scroll through a little bit, but they built some really interesting explorers to see how different parts of the network are being activated for different layers in their network. And I think this is just part of a broader exploration they did here on feature visualization in general. So here's their individual neuron, a whole channel in your model, and then you've got like a whole stacked neural network and what it's finding. So there's some really neat stuff. I'm just trying to they're just trying to dive in and understand how is this model working. So yeah, kind of pretty cool stuff, diving deeply into neural models, and I think what you can see through this is that the model visualization space is pretty open. This is relatively new work. I see 2017. Feels more recent, but that's a few years ago. But there's still a lot of space and new work being done in trying to understand models, and this is really important. Really important now for the future in understanding bias in models and equity in models as AI becomes more ubiquitous. So new novel machine learning visualization and is going to be really important, and this is a pretty open space. So this is just one deep dive into a specific type of model, a vision model, and along that line of understanding how a model performs and like which inputs are driving the score. Some models are hard to interpret, so there's this project called LIME, and LIME stands for I think local interpretable model explanations. Maybe the L's for linear. I have to go check. What do they say? LIME. Oh, they don't say right at the top. Well, I am saying linear because the way that LIME works is, you may have a model of any complexity, like maybe a random forest or a neural network model or a support vector machine model. Lots of different ways to go about it. The problem with each of those that I just mentioned is there's not like a linear way between feature X and the score. So what they'll do is they'll take a bunch of outputs from the model, look in the output space, and linearize the each feature on that output space. So they'll build basically a tangent linear model to your nonlinear model that's locally linear. So your model probably behaves linear if you really zoom in, and the idea is taking a specific point in the model or a specific input, right, that's going to map to an output space. If you vary around that, which features are the most important in moving the output. So a linear approximation of the model can tell you which features are the most important. And so here, right, you're going to get out a feature importance metric. And they end up using diverging bar charts, things like that to display this univariate. So to explain a single prediction for this is focused around an individual input. So that's a pretty cool way. There's other techniques that are like Lime. Another one is called the Shapley value, and I'm not going to be exhaustive on all the different types of model explanation metrics. Want to focus on the viz aspect here. These are just different ways to get values for individual features. And ultimately, right, we're going to have tabular data here for visualization. Shapley, right, a different way to look at the same problem. They're looking at it in a way where they'll kind of consider all possible inputs to the model, and it's more of a numeric approach to try to understand the probability that if you vary one thing, sometimes the features actually vary together. So if you vary one thing, how important is that? Just another way, the Shapley value for any given input value can show you how the features contributed to the score that you got from that. This is one that we've looked at in detail at Mass Mutual to understand how our models for algorithmic underwriting are using input variables to give an individual a particular score. And visualizing that, right, is another challenge. So these are just a handful of tools to dig into that. I wanted to share one that I've worked on in particular, which was this idea of a word shift graph. So I'm going to scroll here. But just to say, this is in 2020, so this stuff is still happening, and I just want to share an example of the graph. So this is what a word shift graph looks like. It's a split bar chart. We've stacked bars on the right side for a generalized contribution graph. There's a lot going on here, and I'm not going to dive in too deep to try to explain how this is working. There's a legend above that I scrolled by. But again, just it's an open space to understand better models for NLP, text type models, for any type of machine learning model, and we can bring all the techniques and tools that we've seen in data visualization to bear to better understand our models and be better machine learning and data science practitioners.